everybody's got their state machine back if you turned it in, and I thought everybody did a pretty good job. I was going to show you the way that I did it. This is not the right way necessarily, it's just a way, but I thought it would help some of you that I wrote some comments on. I wrote some comments on like, I would split it up more or split it up less, or so this is how I would probably do it. I would start my state machine, and then I would go to an initialize state where any startup stuff that needs to be done would happen. And then I would wait on the user to set things and press start. After that, I would do a safety check. And there could be lots of things that are in there that weren't necessarily in the user story. After we know that it's safe, I called this state source on. That involved turning on the X-rays and opening the shutter. So I kind of lumped those two operations into one state. Since it's one thing, we're going to do it together. Then I would have a move state. Then going down here, we have a count state where we're counting the radiation. And then this, I called a time elapsed. We said how long we wanted to count. So after some time has elapsed, I'd move from count. And this state would be optional. Some people would lump it in. I generally don't like to, which is write and display. So that writes the data to a file and would show it on the screen. And then after that, if our angle that we're at is less than the maximum angle we want to go to, we go back and we move, and we do this over again. We just keep looping there. And so I don't go too low on the board here. We'll say if theta is greater than or equal to theta max, we shut down, and that is the end of the state machine. And what's missing is you want on a parallel branch here, we want error or door open with source on. So if the door is open and the X-ray source is on, or if there's any other kind of error, we want to immediately go to a shutdown state. And that's on a separate branch of this state tree because we want it to be running in parallel with everything else that's going on. So are there any questions or thoughts on something like this? I thought everybody did a pretty good job. There are some people, there are lumpers and splitters when it comes to doing this. And there are definitely some people that are lumpers, and all of their state machines that they ever create have 3 states, which are start, run, and stop. And that run state it's kind of a God state. There's so much in it, it's unmaintainable. There are also people that, and I am guilty of this a lot of time, that this state machine might have 30 states, and that's a little bit too complicated, quite possibly. The state transitions could get pretty difficult to maintain. For most state machines, as a rule of thumb, for semi-complicated things like this, I would say in the neighborhood of 7 to 10, certainly maybe 15 tops, is a good number to think about. It's not a hard rule, so you can have more or less, but it's kind of where I try to shoot when I'm doing the design.
So, but what if there is an error occurring during the scanning state? For example, when you scan the sample, the door is open, and then it needs to be shut down immediately.
That's why this is on a parallel branch. Okay. So this is one branch that we're going down and we're running here. Anything else that comes from this dot, it means it's running in parallel at the same time. So if at any time an error occurs or the door is open with the source on, we immediately go to shutdown.
So no matter when the door is open?
Right, because that's all that branch is doing. It actually never goes down this path. It sits here at the beginning and waits for something like that to happen and then goes directly to shutdown. Right. All right, anything else? Okay. Just going to clarify on the homework some. Somebody had a great point that there's a typo where it says hexadecimal. It should be base 16 because we talked about hexadecimals base 16. There's a typo at the top of the assignment. And then in the, can I borrow?
Go ahead.
On the question number 5, with the IEEE floating point representation, there's some confusion on this. So that hexadecimal number that's there, that 40490E56, that is a 32-bit value that you need to convert to a float using the IEEE 754 standard. So that's 32 zeros and ones, and you use that format that we had in the slide to convert it to a floating point. So your answer should be, this isn't the answer, but it should be a floating point number like 1.3725 or something like that. So is that good for everybody? Any other questions on things that were unclear on the homework?
One other thing, there's a quiz associated with the homework. It's going to be a pop quiz, and anytime you're in the lab, you need to be able to read the binary plot like that. Okay, no.
And it is set. I
It's set
checked it
properly
earlier.
right
Yeah.
now.
Cutting the cord,
What's that?
cutting the cord,
We can fix it.
all
The
the
cord's
razor
pretty
blades
simple
are
to
bent.
fix that.
Yeah.
That can be part of electronics,
I'll
hardware,
rewire the circuit.
fixing the cord, and then be able to read
It's gonna become a small
read it
explosive.
quickly.
And the other kind of, I guess, news weather sports thing was I sent out an email that for the next, I think 4 or 5 lectures, we're going to be doing mechanical stuff so that you have some electronics and some mechanics basis to start on your projects now. And then we'll go back and revisit some electronics topics in more detail in a couple weeks. So you won't need your boxes for a few courses. Look ahead on the website. You can see when we go back into electronics, and I'll warn you again. Also, if you are doing your project and starting to think about what parts you need to buy, start sending us the parts that you need. We're going to do a group order to reduce the shipping cost as much as we can and try to get everybody's stuff. So look at SparkFun, Adafruit, DigiKey, wherever you need to buy your parts, and start compiling that list to send to us.
Right, and we'll send out a deadline for when that's gonna be. We're gonna buy the stuff for you, and, we're certainly gonna buy all the big stuff that goes in one order,
Right.
and you're gonna have to guarantee that you make it, if we give it to you. How's that sound, Rich? If you don't make it, then you have to refund us the money.
Which should be $50 to $100. So we could be, it's going to be a big order for the class, right? If everybody spends $100, we're going to be pushing $1,500 with tax and shipping and everything. So it's not a trivial amount, considering we don't really have funding. So, all right, everybody good on that? Okay. So today what we're going to talk about is mechanical drawing. And this is a really important skill to be able to communicate to the shop what you need to build. And I would say for your projects, many of you are going to be making mechanical drawings and taking them over to the shop and working with them. So let's say that this was some bracket that you thought you would need for your project or for something in the lab. That's a pretty complicated shape and a pretty complicated geometry. So how are you going to tell someone how to make that? If you sit down over at the machine shop and you pull out a piece of paper and you say, well, it's square, it's got this angle on it about 30 degrees or so, and they're not going to do it, and Ellis will look at you like you're crazy. What they need is a mechanical drawing, something that fully specifies every dimension, every part about the shape of the object. And we're going to go over how to do this by hand, so some basic mechanical drawings today. And then next week, we're actually going to use a CAD tool, and we're going to be able to model the part in 3D in the CAD on your computer. So make sure you bring your computer on Tuesday. And then we can even look at how to make the drawings from that. But a lot of times, if you send Ellis the 3D CAD file like this, they can plug that into their computer-aided manufacturing software, and those CNC mills will just carve this right out. It's not quite that simple, but it's a lot easier than having to go from somebody's napkin sketch. And drafting until modern CAD tools has been done with, there were draftsmen that this was their job, rooms of them at big companies like Boeing that were drawing parts. And they would have these big drafting tables, and a lot of these tools are handy to have, but I would say very few of us own some or any of them now. For example, I don't know that anybody has a dusting brush for their drafting at home handy. But things like protractors, of course pencils, and maybe some of the scales, you can buy at Hobby Lobby is where I got this, which we have one of those in town over there by Applebee's and everything. You can buy this for like $6, and it's got a protractor, a ruler, and a couple of squares. So you've got a 30 and a 45-degree square in there. So those are really handy for being able to do your drawings. A compass is nice for doing radius and that kind of thing. Having a French curve is handy, but I'm going to assume that most people don't have those. And a lot of time, if you're making a sketch, because you're going to make a one-off thing, you can sketch it in, dimension it. It'll probably be good enough for what the shop is going to need in our case. And these hand drawings, you think, well, what we're going to do is probably pretty crude. This is a hand drawing by a draftsman. So draftsmen were artists, and they made, this is what's called an exploded drawing, where you see the device busted apart into its pieces so we can see how they go together. It's an assembly drawing. So each of these pieces would have had a separate two-dimensional drawing that tells the manufacturer how to make that part. And then this assembly drawing would show somebody on the line and say how to put it together, or somebody that's repairing it. But now I would say the art of finding people that can make a hand drawing that looks that good is all but lost, most likely, because we all use computer-aided design now.
But I guess it's the origin of all the ideas, like in things like Acrobat, is that the idea of layers.
Yeah.
Because this isn't, when you did things by hand, this thing here you had to make completely from scratch. You had to put it together with anything else, right? You can guess, like I've got all these individual things, and then I want to show them together, and I do that with this.
Right.
Layers.
Well, and there were in a lot of, I would say more blueprint type stuff where you would have a base drawing and then clear, I don't know, what was that material called?
Mylar?
Yeah, it's like a Mylar sheet that you would pull down and you could actually physically put layers on like you can in Illustrator. But for a lot of what we do in the lab, something like this is probably good enough if you're making one. If you're making a bunch or it's a really complicated part, I would say you should probably still put in the time to do it in a computer tool. But this is a pretty simple part. And if you take this sketch over there, it's very likely that you would get back exactly what you had in mind. Okay, maybe this is only one view of a three-dimensional part, but it's a good start on a complete drawing anyway. So there are things in here like some dimensions. Here they say this is a 5/16 screw, 1 inch deep. There's a center line here, so we know that that's the center of the part, and all dimensions can be relative to that. So it's not bad, and it's something that would take you 10, 15 minutes to do. They do get worse from there. You can not use a straight edge and just freehand. In this case, it would be a little bit harder for them to possibly figure out exactly what you were going for. But it could still be useful because this isn't a really complicated part. This is a bent piece of metal with a contact on it, right? And there's, so this says 0.1 radius would be the size of that. And one of the things that's on this that I like, and the reason I put it in here, is there's some instructions. Like it needs to be out of copper, because if you don't tell them, and well, they probably won't assume, or you might get something back that's the completely wrong material. Or it could be beryllium copper, yeah, actually, it could be. Should be a little e, but. It's, in drafts, a lot of times, too, you'll see people do everything in all capitals. Hand lettering was a big thing that you had to practice. But yeah, there should be little e, actually. And then they have a little description of it. This is glued. There's a bend radii specification in here. So a lot of details on how to make this little contactor. And this is something like you would do, this is an Autodesk, AutoCAD drawing. AutoCAD would take a little bit of time to get used to, but once you kind of know the basics of it, you could make this drawing in AutoCAD in 15 minutes or so. And it's very precise, right? You hand this to them, there's no problem. We've got an isometric view, a right view, a front view, and a top view. Everything's nicely dimensioned, and we're good to go. It's just missing the title block down here that says some important things like who designed it, what it is, what the scale is it a one-to-one drawing, and that kind of thing. So this would be a simple part that you could send. This would be the title block that I was just talking about. And there are some important things to note in here. These lines here that are generally thinner and broken are centering lines. So they're not a physical thing on the part. It's to help the drawing and show that indeed those holes are along the center of the part. These dimensions are all very nicely done. We'll talk about how to do dimensioning in a little bit. They say that all dimensions are in inches because you'll notice we don't write the units after the dimensions on the drawing. And there are tolerances. Specifying tolerance, again, we'll talk about it at the end, but it's a really important thing to do here. If you've got two places after the decimal, the tolerance is plus or minus 20 thou. 3, the tolerance is plus or minus 1 thou. Otherwise, the machinist would probably assume, and I know our shop assumes, that you need their highest tolerance if you don't specify a tolerance. And the highest tolerance is expensive. So you want to specify low tolerance where you can deal with it. And so it says the material here is brass, it's got a date. Scale is really important. This is a 1-to-1 part if it were not blown up on this projector. And sometimes if the part's really small, we'll draw it in a large scale, or if it's a really large part, then we'll reduce the scale so it can fit on a piece of paper or a larger piece of paper. But it's really nice, if you can, to draw the part 1-to-1. So the machinist, as they're going along, this is exactly what the part should look like, and this is what I've got in my hand. And there'll be a lot of markings. On this one they actually didn't use too much jargon. For example, here they actually said 1/2 drill, 2 holes. But you'll see these on a lot of drawings. So DIA or D or an O with the slash through it, for example, is a diameter. Chamfer, CHAM. All of these you'll see, and this is a handy table I put in the slide so you can go look stuff up on it if you need to make a drawing, or if you're looking at a drawing and don't understand exactly what something means. So we're going to look at this part and use it to illustrate some good drawing principles. This is a relatively pointless part. It's just this block of material that's got a high part here and a little step here, and it's flat on the bottom. Maybe you could make this some kind of jig or something like that, but it's got some interesting features. So this is an isometric view, what I just showed you, and there are 2 types of drawings. So there's isometric, and then there are orthogonal drawings. The isometric gives you an idea, kind of a perspective of what the thing's going to look like when you're holding it and looking at it on the 2D page. But in terms of if you hand the machinist that, it's not incredibly useful. They need the orthogonal views. And it's generally drawn with 30 degrees up from the horizontal. But if you think about having a cube around this, so imagine building a plexiglass box and setting it over your part. And you're going to look down or in from each side, and you're going to trace exactly what you see. So from the top, we see the outside, there's the step, and there's this part that's jutting up, but it's just in 2D. And on the front, there's the part that's coming up, there's the step, there's the base. And on the side, we see the base, the step, and then the part that's coming up. Now, if you were to take your glass box apart, or if this were paper or something, you're cutting it and you unfold it, those are the top, front, and side views of the part that you're going to want to draw on the mechanical drawing. You're going to go ahead and give to the shop or take into your meeting with your advisor. And so this part is it's a little shaft that's got a turn down bit here. So it's only going to take 2 views to completely describe that part. You don't always have to use 3. This is especially true on cylindrical parts. So we've got a side view where you can see how long it is, how long this turn down part is, and then an end-on view where we see the diameter of the turn down is 650 thou, and on the outside it's 1 inch, or millimeters if this were a metric drawing. Does that make sense to everybody? Looking at drawings takes a little bit of time, and especially when we start putting some of the more complicated features on. So if you look at this part, you think about your glass box, there are 6 drawings that you could make. This is a little bracket. This is something that we could conceivably see building for the lab to hold something in. So put a screw through there, and maybe it holds something as a clamping bracket. So there are a lot of different, so 1, 2, 3, 4, 5, 6 drawings that we could use. The most useful turn out to only be these 3, the top, the side with the plate, and then end. You could make the rest of the drawings, but it would be a little bit redundant. Now, there's a first angle projection and a third angle projection when you're doing mechanical drawings. And it depends on where you are and what company you're working with, or what your machinist likes, as to what you're going to use. So if you imagine you're putting your part in this space, if it's in the first quadrant, that's a first angle drawing. We use those primarily in the US, and I think Australia uses that. Pretty much everywhere else in the world uses third angle drawings. And I'll show you a demo of that. All right, so we've got our part here. In the first angle, it's up here in this quadrant. So we have a projection on that side, on the front, and on the bottom of it. If we're down here in the third angle, then we have the top, the back, and this right side of the part. So here we're looking at the left side of the part. If we're looking front on, here we're looking at the right side of the part, if we're looking front on. So is that sort of clear? This is the best graphic I could find to demonstrate it. And you just have to specify. It's pretty easy to switch back and forth between them, but you have to specify what angle projection you're using. And then, of course, you can unfold them. So we've done our drawings. We're cutting the box and unfolding it. And now what you'll see is the right side view is on the right of the front view in third angle. And in first angle, the front view and your side view is going to be on the left side of it when you actually have the drawing projected on your piece of paper. So a quick way to tell if it's first or third angle is in a first angle drawing, the view will be to the right. In a third angle drawing, the side view will be to the left. Is that good with everybody? A couple confused looks. All right. Well, if you have questions, stop me at any time. Other thing is, when you're doing a drawing, draftsmen would generally have a lot of different pencils with different weights and different leads, so that they could make lines of different thicknesses and different darknesses. In CAD, that's easy. We can do dashed lines, we can do colored lines, we can turn layers of lines on and off. But when you're doing things just on your own, you can try to make light lines or dark lines. So for example, a hidden line might be, or a line that's like where these two surfaces intersect might be a little bit thinner than the main outline of the part. A hidden line like these, where this hole, we can't see it strictly in the side view, but we want to notate that it's there, could be dashed, for example. And then the center lines are also generally pretty thin. In some cases, you'll want to project the part on a plane that is not top, front, back, right, left, bottom. You'll want to do a weird projection. Those are called auxiliary plane projections. And say we've got this part where we have a hole for some kind of dowel or shaft that's going to come down at an angle. Well, in the top view, this is going to look like an oval. And maybe that's not the most useful thing to show our machinist and specify it's a round hole. It's true, but we can make an auxiliary plane view. So from the side, we see the hole going through the part, notated by these hidden lines. And then we can do a view as if we're looking down on that angled plane, where now we have a nice round hole. Notice the continuation of the center line, so everything's lined up. We have this nice round hole that we can then notate. When you have a lot of features that are inside the part, so holes or passageways, something that's really common in rock mechanics is we have fluid passageways in, say, end caps or in blocks that we're using to hold samples. You can show them with a section. So a section is actually kind of like a geologic section, right? We're going to pretend like we take the part, put it on a saw, and cut straight through it. Or if you had the water jet, I suppose you actually could do this. You would destroy your part. And then you're going to draw exactly what you see there. So on the part, this is saying that we're taking a section from, generally we mark it A prime, or you could just say A to A. And then down here below it, we're looking at what that part would look like. So these diagonal lines means that's all solid metal. And then here we've got the hole through the part. And a lot of times you'll see people notate it in their isometric view as well. with a light colored plane going through. Sections do not have to be straight lines, and in fact there's a lot of cases where they should not be straight lines, I would say. Let's say we have this part, it could be a flange for a pipe, let's say, and we have 5 holes, and we want to take a section through it to show maybe those holes have a complex counterbore or something that we want to point out, or we just want to show that they go all the way through maybe. Well, we could take a section straight across like this, but that looks pretty weird, and it's maybe not the most useful thing, because here we're showing that there's no hole. It's obvious there's no hole there. And then here we're showing a through hole. So you can break the section, and in this case, in cylindrical parts, it generally makes sense to break the section at the center of the part and have it go through the center of both of those holes, and then you show the cross section like that. We can also do aligned sections, and these can get pretty difficult to visualize until you've looked at the part for a while. In this case, we've got a block that has several pockets in it, so several areas where material has been removed. And the most useful thing to show, if I wanted to show the machinist how deep those pockets need to be, for example, I could take a section through there, and a section through there, and a section through there, and each of those sections would only have one pocket shown on it. It's not a very efficient use of my drawing space, and it has a lot of redundant, unnecessary information. Whereas we can take our section line and break it. So we have these vertical lines where it's like taking this and shifting it up or shifting it down. So we go over here, then we go through this pocket, then we go through this hole. And in section view, it would then look like that. These are pretty common to do on complicated parts, though. The section madness doesn't stop there, because you can also rotate features in aligned sections. So in this part, we've got some kind of squarish thing with a circular boss and a hole in it, and these 2 little mounting ears with holes in them. The best kind of section view that we could draw, the most descriptive section view, if we just draw a section across here, we get this hole and this hole, but we don't get either of those. We could draw a section across there, but that's kind of pointless. We get a bunch of weird things in here that we don't really care about. So what you do is, with this arrow, we're notating that we pretend we take this ear, rotate it to this section of the part, and then take a section all the way across. So this represents this mounting ear, this represents the rest of the part. So it's another kind of aligned section that you'll see sometimes. Sometimes you'll see half sections, and in 2D I don't like to use these as much as I do in 3D. There are occasions, though, where this half of the part is untouched. It's exactly as you would see it in a traditional side view, and then we're going to take a section from here to here and show the section. So maybe this could prevent you from having to have a broken out section. If the part is symmetric enough, you can have a side view and a half section. That's all you need. But in 3D, sometimes it's nice because you can put 2 half sections in. So like for this part where we have this, some kind of slot that something's going to go into, and a hole that's got this boss sticking out, we can put a half section in one plane and a half section in an orthogonal plane and get all of that information in one view. It's an easy way to convey to the machinist what we're doing. We're almost done with sections. This is the biggest chunk of mechanical drawing because it's a really useful thing, and there's a lot of people that have thought of creative ways to do this. So let's say we have this model. It's some kind of bracket a shaft is going to go through, and in the center somebody put this this bump, maybe to give it some structural rigidity, and we want to take a section right there to specify the shape of that cross section, that bump. Well, you could do like this and then break out a section, but you don't have to. You can use what's called a revolved section, which this would be the side view of the part, and then we take this, rotate it so it's in the plane of our view, and that's the revolved section, because the information that we're getting from the side view isn't very useful, and there's a lot of redundant visual detail there. So again, this will be the section. We rotate it into the plane of the view that we want to put it in and draw it on. Is that good for people? Confusing? All right. Another common tool, I like to use this a lot in my drawings, is the detail view. If you've got a big part that has a small complex area, or even a small part that has a small complex area, maybe 1-to-1 isn't good enough to show what you need to. So say you've got a part that's a couple meters, and then you have a feature that is a few thousandths of an inch. Well, you can't draw it in even a section view and get anything useful from it. So you draw a circle with these arrows, give it a detail number, and then you blow it up out here at a larger scale, and you can do dimensioning, annotations, whatever. So in this case, it's a section. We're cutting through some assembly, and then we're actually detailing part of a section here at a 4-to-1 scale. So for example, on a lot of you are familiar with the side blocks for the biax. We could have a drawing of the blocks. The teeth are going to be pretty small, so you could have a detail view that blows up the teeth. Probably not quite necessary, but it's nice to make life easy on your machinist. Things like threads, even in 3D modeling programs, we can model them where it actually has the proper thread pitch and 60 degrees, all that, but we generally don't. We're going to use a tool like a tap that you all have used now and run through there to create the threads, so we schematically show them. We can use these crossed lines like that, so we've got a long line, a short line, a long line, a short line. You can even just use a line like the hidden line to specify the inner diameter of the thread, and then you have the outer diameter of the thread. It's really all you need to do, and then you notate what the thread is. So you would put a note on here, and you would say this is 1/4x20 UNC thread. Another example, this is a bracket that's got a hole through it, and then we've threaded that hole. So this would be the drill diameter, that inner part, and then specifying 5/811 UNC, Unified National Course, remember we talked about in threads, 650 thou deep. And this is what it looks like in cross-section. Or, sorry, this is what it looks like from the side, and then they drew hidden lines. They didn't actually do a section here. And you see that the threads do not go all the way through the part. That's why they specified 650 thou deep here, because they're only going partial depth. That is not uncommon in some parts to have that. Another thing is, let's say we're making a drawing of something that's got a rod that's connecting things, and it's pretty long. So even let's say that we're drawing a load frame. This is still smaller than a load frame is going to be laterally, let's say. And we've got these big bars that join our load frame together. If we were to draw this at 1-to-1 scale, we would need a board that's much longer, and the bars are pretty uninteresting. They're round, cylindrical bars of metal. So we can break them. There's a bunch of different notations. In this case, they're solid, so the marker doesn't die. You do like that. You don't have to be a great artist, especially, I haven't really seen people use this tubular one where you can see the fill and you can see the hollow inside, unless they do a computer drawing. But it's a way to just say that you left out a bunch of material that's the same in between. All right, now on to dimensioning. This is the dimensioned isometric view of that part that we looked at in the beginning. And you can sort of figure out where everything is by looking at it in 3D. Okay, what's this? Okay, so that's 5 back from the face of this to that. It's not necessarily the easiest thing to look at, though. We generally don't dimension isometric views, just the 2D views. The dimensions need to describe every feature of the part, but no more. So you want to use the minimum number, provide the least amount of visual clutter of dimensions that you can to describe how to make this part. So for example, these are all the dimensions that are needed to do this. I don't need to dimension how wide this is because I dimensioned an overall length and the things on either side of it, for example. And you can do it in parallel or in series. Depends on what's important to you. So the top part here is the top part is dimensioned in series. So we specify the dimension to the center of this hole, and we specify the dimension to the bottom of this, and then we specify the dimension to there. And they're all chained together. The dimensions down here are specified in parallel. For example, we're specifying from one edge to every feature on the part. It all depends on what tolerance is important to you. Everything has a specified tolerance. So let's say it's plus minus 5 thousandths of an inch on each dimension. Well, here, this is plus minus 5 thousandths. This is plus minus 5 thousandths, so this is plus minus 10. This is plus minus 5, so this is plus minus 15. You get an accumulation of tolerance errors that can happen. But maybe what's really important is the exact width of this, not how far it is from either end. Then this would be the kind of drawing you want to use. If what's really important to you is the actual from one end of the part to here and from that same end of the part to the hole, maybe not so much between the holes, but from one end to the feature, then you dimension in parallel. And this would be an over-defined part, kind of like I showed before, but another example of it, where we're specifying the overall length of the part, and then we're specifying from the edge to this hole, from there to there, and from there to there. So this would be a series dimensioning, and this looks like somebody started doing a parallel dimensioning job and didn't finish. So this dimension is totally unnecessary. Here's what I was talking about was tolerance. This relative cost is relative because it's not adjusted. They would have to update this every time they publish the book for inflation and shop rates and all kinds of stuff, and new techniques. But tolerance in inches, so we've got 5 thou down here, 30 thou up here. You can see the relative cost can take a really big jump as you go smaller and smaller. So maybe it's okay if your block is even 100 thou over size in one direction, and just the holes in it need to be precisely dimensioned. You can save yourself a lot of money. You can specify tolerance in a few different ways. A lot of times you'll see either plus or minus or a plus minus. This is very common in assemblies that are going together. This is saying this can not be any longer than 4.012, but it can be up to 2 thousandths of an inch shorter. So that's pretty common. Diameters, plus minus is pretty common. The other way is people specify the range that the part has to be in. And maybe it's an asymmetric range. Maybe it's minus 3 thou plus 1 thou or something like that. So you could just put the range in. And generally if you're making a lot of these, there will be what's called a go, no-go tester that has the minimum and the maximum size, and you try to put the part in and make sure that it fits in the range. All right. And on this drawing, going back to it, like I talked about earlier, they have the tolerances down there in the corner, and they're using the number of decimal places to specify it. That is how, if you send a drawing, it's on the machine shop website. If you send a drawing to Ellis and you don't specify tolerances, they will go by number of decimal places. The one thing that we're going to do, we've got probably about 20 minutes by the time we get this done, is before next week, go sign up for an OnShape account. It's free. It's onshape.com. The link's on the website. We're going to use this next week to actually draw some parts in 3D. This is an online 3D CAD tool. It's like SolidWorks, but it lives online. So we don't have to install SolidWorks on all of your machines, which is good because SolidWorks is Windows only and many gigabytes, and the licensing is difficult through the university. You can use this for free as long as your designs are public, for as long as you want. If you want to have more than a few private designs, you have to pay them. And I think it's about $100 a month, so $1,200 a year, which for a CAD tool like this is absolutely dirt cheap. And then we're going to make a mechanical drawing. There's an activity on the website. But before we do that, I want to go ahead and give you a taste of what OnShape is like. So you can kind of see how powerful this is. They've got a lot of tutorials on their website that you can feel free to explore if you get bored this weekend. Let's go ahead and The other thing, if you have a mouse that has a scroll wheel, bring it. It makes, using a trackpad in a CAD tool is something that is crazy making very, very quickly. So I'm going to show you a couple of parts and then some assemblies. Let's see. So this is a 3D model of a part, possibly. There we go. So we can spin it around, we can look at it. In these tools, I said I wanted to make a section. So I'm going to say that I want to make a section, and then I can drag this back and look at section views of the part. You can even do half sections and all kinds of fun stuff in here, and broken sections. Draftspeople 20 years ago would have killed for this.
So all of this is online.
All of this is online.
You don't need to download the software.
No, there's no software to download. They do have an iPad app that is not bad. It's kind of hard doing this in an iPad, but and the nice thing is you can combine multiple parts into assemblies, which I'll show you an example of in a second. And then this same tool, we can use it to make drawings. So this is the mechanical drawing of that 3D model that we were looking at. And if I update the 3D model, the drawing automatically updates. It's wonderful. It can save you a lot of time. And for example, in this model, you can see that I've got a top view that's dimensioned with some notes, and then I have a section view over here. Show you an example of an assembly. This is one that a lot of you will recognize. So this is going to be a bracket that was designed, and we've had this made. So I sent this CAD file off, and this part came back. So it directly translated from CAD very well. That bracket, but to design that bracket, it was going to mount on some of the equipment in the lab, so I had to model that equipment. Things like the side block of the biax. You can see there's some teeth there. A center block. Got teeth on both sides. And I put a couple of holes in it. I actually modeled the plate for the base of the biax and went up into the lab and measured the size of the support blocks that we have. And then you put all of these pieces together and you make an assembly. And so now I could see how everything was going to fit together. I could say, does this need to be taller? Does this need to be shorter? You can do some motion analysis. So I can move this around. I can say, what if I shear down here? Then how do things look? It's like, okay, well, that's going to be a problem. If that's there, then it's bumping into that. So that's not good. We have a conflict there. So you can save yourself a lot of design headache. And things like these screws, those are the exact screws that I bought to use for this. You can go to McMasterCar.com or a lot of the places where you're going to buy hardware, and you can download the CAD model for the hardware that you're going to buy directly from them. So I didn't draw those screws. I just downloaded them, and now my model has the exact screw that I'm going to use. So I can make sure that the head's not too big or too small, or that the heads are going to hit. So you can save a lot of time. All right, so I've got a bag of parts. There are some nuts,